Take it away, Max.
Okay, thank you, Lara, and thanks to the organizers for letting me speak at this special conference. And indeed, I will talk about Instanton corrections and emergent strings based on two works I was doing with Florent Baum and Fernando Marchesano in Madrid, and a recent work that hopefully appears soon with Daniel Kleber, Sang-Jun Lee, and Timo Weigand. The good thing about being the third person in the swampland section to speak is that I don't have to lose many words about the swampland itself, but I will just recap the important swampland conjecture for this talk, which is the swampland distance conjecture, which roughly states that at infinite distance in modular space, an infinite tower of states becomes exponentially massless in Planck units. And this is, from all the swampland conjectures, the only one that we will use here. And this conjecture motivated detailed studies of asymptotic string complexifications, about which Irene already talked in her talk, in order to understand the realization of the swampland distance conjecture in string theory. And there's been a lot of work, and I am sorry to anybody I forgot to cite here. Okay, so how is the swampland distance conjecture realized in string theory? So it's mostly studied in the vector model space for the NF2 complexifications of type 2A and type 2B string theory, and I think these were also the favorite asymptotic limits that Irene referred to. So they're actually nice in these cases to analyze the swampland distance conjecture, since the modular space is classically exact itself in type 2B, or at least mirror dual to an exact modular space in type 2A. So one can actually make classical statements that also carry over to the quantum regime. Then the infinite distance points can be completely classified, which has been done by these people. And the tower predicted by the swampland distance conjecture is realized by a tower of wrapped D-brane states that can become masses at the infinite distance point. So example, more or less easy example, is the tower of D0 branes and type 2A string theory in the large volume limit. But as Irene already pointed out, that this tower looks much like KK tower for higher dimensional theory, and that we actually run into the decompactification. In this case, it would be the decompactification to M theory. And Lee and last year, they analyzed different kinds of this infinite distance limit in stringy setups, and so that this is actually, this happens in more general or also in different setups. And also these people saw that the KK tower, being the dominant swampland distance conjecture tower of states, is actually quite a general pattern. So, but are there other kinds of limits of infinite distance where we don't get a KK tower that gives us the predicted tower? And there were these people in a series of papers, I think 5, that were quite active in looking at limits where we actually have a tensionless string. So for instance, the first example was, if you consider F theorem in elliptic Calabi-Yau threefold, you can actually classify the infinite distance limit that satisfies this constraint that the Planck to string scale ratio is constant. And what you get in these limits, in these cases, is that actually the base of this elliptically fibered Calabi-Yau threefold can be seen as a rational vibration, where the infinite distance limit corresponds to the limit where the fiber of this rational vibration shrinks to 0 size. We now wrap a D3 brane on this curve C0. This is actually dual to a heterotic string, to a critical heterotic string on a K3. And the tower of states that realizes the swampland distance conjecture is the tower of massless string excitations. And then the main part of this work was also to see that if and how the string excitations of this tensionless string realizes the regravity conjecture. So a similar story can be done if you consider, or if they consider M theory and Calabi-Yau threefolds that have either a K3 or a T4 vibration, and then look at the limits in the Kähler modular space where the fiber vanishes. And there you get actually 5D strings that become tensionless, which are again dual to critical strings, either the heterotic or the type 2B string. So in all these limits that were considered so far, or that I mentioned so far, the limits of the tensionless string are such that the string tension and the KK's
Sorry to interrupt you, but we're getting some scratching noises from your microphone.
Oh, sorry, maybe. Okay, I'll keep it like that. I hope it's better. that the string scale and the KK scale the same, so that the string tower and the KK scale tower in principle compete with each other to give the swamped distance tower. But since the string spectrum is denser than the KK spectrum, which is just due to the fact that this grows like n and this grows like n squared, the string tower will be the dominant tower for the emergent string, for the swamped distance conjecture, which motivated these people to formulate the emergent string proposal that any infinite distance limit that is not a decompactification limit, so that is an equidimensional limit, reduces to a weakly coupled string theory, and that the asymptotically massless states of these strings is the tower of the that is predicted by this or that is required for the swamped distance conjecture to hold. So until here, all the examples that I gave, we could just look at the Kähler moduli space, purely geometric, purely classical. So you could just take a limit, okay, I shrink a curve or I blow up a curve and then see what happens. As in these moduli spaces that were relevant so far, no quantum corrections occur. There's the exception of the type 2a vector multiplate moduli space that were also considered by these people, where actually these quantum obstructions are important. But what about limits in moduli spaces that are not classically exact and also are not directly via mirror symmetry related to a classically exact moduli space? So this will be the part of my talk, where I will, in the first part, will consider the hypermultiplate moduli space of type 2b string theory on a Calabi-Yau threefold, and I will discuss the interplay between emergent strings like that are the content of the proposal I mentioned before, and Instanton correction, which is the content of the work I did with Fernando and Florent. And then in the second part, I will talk about also quantum obstructions to classical emergent string limits, but now in n=1 moduli spaces of F theory in Calabi-Yau fourfolds. And this is this work with Daniel, Sanju, and Timo that hopefully appears soon. So, but let's go first to the type 2b hypermultiplate moduli space. So we consider type 2b string theory compactified on a Calabi-Yau threefold X, and then it's now well known that the hypermultiplate moduli space is spanned by the complexified Kähler moduli, the RR axions, and the dilaton. So we will be mostly interested in the saxionic directions because these are the ones where we can get an infinite distance, and mostly so the saxionic directions, the saxionic components of the Kähler moduli and the axial dilaton, and mostly forget about the axions in this work. So if we talk about infinite distance, we need to know what is the metric that we're using, and it is known since the 90s that for this, that classically, before we add quantum correction, the metric is actually related by the C map to the type 2a vector multiplate moduli space by just embedding the type 2a vector multiplate moduli space is totally geodesic submanifold in this quaternionic scalar manifold, and adding the 4D dilaton. So, but the problem is that if you're not in the weak coupling large volume limit, the Planck to string scale, if you're not in the weak coupling large volume limit, the classical approximation to the hypermultiplate moduli space is not that of a good approximation, because quantum corrections affect the hypermultiplate moduli space severely. And also this limit, where we have a nice description in terms of the classical metric, for instance, is actually not that interesting, for instance, in the swampland philosophy, because the Planck to string scale ratio diverges. We get we decouple gravity, and this is not what we want to analyze our swampland distance conjecture. So we want to take other limits, but here we have to take non-perturbative corrections into account. And in particular, this will be here d instantons. So, okay, we have to look at, if you choose a path in our moduli space that we think, okay, this will lead us to an interesting infinite distance limit, we have to see what are the corrections to this path in moduli space. And depending on the chosen path in moduli space, different kinds of d instanton corrections will become relevant. So, and the task is then to incorporate these corrections to the moduli space into the physics. And to do this in a somehow manageable way, we have to choose our path that we want to go in our infinite distance wisely, I think. So one interesting limit, which still has manageable quantum corrections, is if we take, for instance, the large volume limit, where we scale up all volumes of our color BR homogeneously and go at the same time to strong coupling. So this was also the trajectory that we already considered in an earlier work last year, where we were interested in looking at the effects for the effective field theory of the instantons. And the nice part is that this is a geometric limit in the metric of the hypermultiplet moduli space, as we keep the 4D dilaton and hence also the Planck to string scale ratio constant. So, but in this limit, of course, we have to get instanton corrections, and we see that we most importantly get D-1 instantons and D1 instanton corrections that will, in the asymptotic limit that I made a sketch of here, will heavily correct the moduli space geometry. So the D-1 instantons are the leading corrections, and the subleading corrections will then be the D1 instantons. So we have a towers of instantons that are correcting the moduli space in this limit that we choose significantly. So together with the instantons, we also have strings that become tensionless already classically. This shouldn't be a surprise, because if you just look for instance, at the D1 string, it's very easy to see that actually, if we go to strong coupling, also the tension of this D1 string decreases accordingly. So if we then plot, for instance, the tensions of the fundamental string, the D1 string, and for instance, the D3 string that is wrapped on some curve and the KK scale, you can roughly divide the part that we have into three regions. This is the region where we could still trust our classical description. Here will be the region where the D-1 become important, and here finally also the D1 instantons. And we see that also the tensions of the string behave accordingly to the instantons that become important. So but we already see that the third region of our moduli space is problematic, as here the KK scale is parametrically larger than the lightest string scale, which in this case is the D1, the tension of the D1 string. So the question is so in this case, if this would be just true like that, one could think of just decoupling all the KK tower from the string, and then we would have just a 4D critical string, which seems to be a contradiction. So somehow this third region has to be obstructed by quantum corrections. So what kind of quantum corrections can we have in this hypermultiplet moduli space? So these are, as we saw, we just have along our particular trajectory, we just have D-1 and D1 instantons that become important. This makes our life much more easier because we don't have to worry, for instance, about D5 instantons, the NS5 instantons. So classically, the Planck mass is given by the 4D dilaton. The Planck to string scale ratio is given by the 4D dilaton. And this can actually be described by a single function, this chi, which is just inherited and essentially from the type 2a vector multiplet moduli space. But if we add quantum corrections, this chi is actually the coordinate that gets corrections and will deviate from its classical values. And one can actually calculate these corrections from the perturbative and non-perturbative alpha prime corrections that are already present in the type 2a vector multiplet moduli space, SL2Z covariantizing, and then getting this expression for the corrected 4D dilaton, so to say. So the quantum corrections change the 4D dilaton, and essentially the change is encoded in how many number of instanton species acquire a small action, because then this term becomes of order 1 and contributes significantly to the classically constant 4D dilaton. So we need to know the number of instanton species and species that acquire a small action to quantify the instanton corrections. At the same time, if this number now grows, the Planck to string scale ratio, which is encoded here, will also change and will essentially grow with the number of species, so that the string scale in this case can be interpreted as a species scale somehow. But we already see that our path in moduli space is obstructed due to quantum corrections, because we chose a path in the beginning where we kept this classically constant, but this apparently is not compatible with taking into account the quantum corrections. So we saw that this limit is obstructed, but we still have some open problems. So first, how to evaluate the instanton sum. So how can we actually account in a good manner for the number of species that become important, the number of species of instantons that become important? What happens to the tensionless strings under the quantum corrections? Are they stable? Does their tension also changes? And what, most importantly, what happens about the hierarchy that mk is, the kk scale is smaller than the string scale that happens in this region 3. So to solve this thing, we note that so far we assumed our hypermultiplet moduli space to arise from the effective field theory that comes from the F1 string, because this is just what gives rise to the hypermultiplet moduli space. But we already saw, and also the string scale, the ms decreases as the number of species of instanton species increases. And now also the lightest string is not anymore the F1 string, but it's the D1 string. So we should actually look at the theory generated by the lightest string. But this is not a big problem for the D1 string, since we know that it's just S-dual to the F1 string. So it might, to solve this problem, might be dual limit. But apply S-dual to this entire limit, and just applying the S-duality transformation to the limit yields us to the weak coupling small volume limit. Again, we have corrections to the hypermultiplet moduli space, but since chi was by construction covariant under S-duality, this should be just the S-dual avatars of the instanton corrections that we had before. And these are just now perturbative alpha prime corrections and worldsheet instantons, essentially. So we see that through S-duality, we actually go to a duality frame in which everything becomes more manageable, because we now have only the corrections that are already present in type 2A vector multiplet moduli space. So actually the limit that we go to is a limit where the type 2A vector multiplet moduli space and the type 2B hypermultiplet moduli space align again. So now we can use what we know for the type 2A vector multiplet moduli space, in particular mirror symmetry, to effectively describe our limit in the hypermultiplet moduli space. But of course, as I said before, we're not in the nice vanilla region in the large volume limit where actually mirror symmetry, where the mirror map is just given by the leading log solutions of the Beaker-Fuchs equations. But we also have here the quantum corrections, which are these order Y corrections that we get to the large volume limit located at Y equals 0. So if we now want to go classically to the TA equals 0 limit, this essentially says we go to the Y order 1 limit, where this term dominates over the log term. So, and then the important point is that taking into account these corrections of order Y tells us that going to this limit, which classically we would say, okay, this is a limit where where some volume shrinks to 0 size, does not necessarily correspond to TA, so to 0 volume anymore. And here it's even worse, because we want to shrink all Kähler moduli at the same time. But this point, as you can see, if we analyze, for instance, cases with a small number of Kähler moduli, does not belong to the moduli space, because some curve will always acquire a non-zero quantum volume, and in general, you need to blow up at least one of the curves. So the limit in hypermultiplet moduli space is actually indeed obstructed, but we can even say more, because we can now, through mirror symmetry, can quantify the extraction and see that the quantum Kähler moduli, if we want to scale them homogeneously, asymptote to a constant value. So the corrected limit, by the quantum corrected limit, can actually effectively be described by constant volume and a weak coupling limit. So we see that we get a weakly coupled fundamental string, because in this case it is now the F1 string that becomes tensionless, because we applied the S-duality at finite distance in Kähler moduli space, because we just stay at a constant quantum volume of the curves. But we're still at infinite distance, which is good, because we have a we have a fundamental string, we have a critical string that becomes tensionless due to the weak coupling limit that we take at the same time. So by S-duality, we can translate everything back to the original duality frame, where it would have been much harder to actually get this obstruction, and see what happens to this hierarchy that I say. So what happens to the scaling of the mass and string tensions after the corrections? And what we actually see is that if this is the classical picture that I showed before, what we see is that the quantum corrections ensure actually that this region 3 is absent or ceases to exist, and that such that the lightest string tension and the KK scale in the asymptotic region scale the same. So we see that the emergent string conjecture in this case is satisfied. But as I said, this is a very particular limit because we wanted to have a limit where we have somehow control over the quantum correction. So, and the crucial ingredient was that, again, we can map everything to something where we can actually make calculations by mirror symmetry. But so what about other limits in hypermultiplet modular space? So in general, it's all kinds of Instanton corrections can appear. And so this makes a complete classification and a complete analysis of this quite difficult. But one possibility that is also viable is if X is elliptically fibered and we go to the limit where the fiber shrinks to 0 size while the base blows up. Because this point is nothing but the initial limit that we had in disguise, because it's related to the initial limit by a Fourier-Mukai transform, which is in this case nothing but in stringy Kähler modular space as shown by these people. Then we know that the corrections that were captured by this chi are invariant under monodromies in stringy Kähler moduli space. And so we get again a quantum emergent string by this, where I say quantum emergent because we need again the 3 instantons in this case to make everything work that are wrapped on the fiber and which are again dual to the fundamental type 2b string. But what about other setups? So because I just talked about type 2b hypermultiplet space and n=2 supersymmetry, we saw already that the quantum correction and the emergent strings are closely related. And in fact, also they are needed to have a sensible and emergent string limit, because otherwise we could decouple our string from our KK scale, and we would have a critical string in 4 dimensions that doesn't know about the compactification. But what about strings in other modular spaces that receive quantum corrections? And in particular, what about n=1 cases? So these n=1 cases, besides corrections to the modular space itself, non-perturbative superpotentials can be generated. And in general, n=1 cases that don't come from n=2 cases, they also will be generated, as shown in this recent paper by Palti, Waffa, and Weigand. Non-perturbative superpotentials might also obstruct infinite distance limits by just saying, okay, as shown by these things, by these people, by saying that, okay, in the asymptotic limit, we have a diverging potential and scalar potential that dynamically obstructs the limit. But also in this case, how are the quantum corrections related to emergent strings? So for that, we first look again at classical emergent string limits in F theory and Calabi fourfolds, which have also been looked at by Lerche and Weigand in the beginning of last year. So again, infinite distance limits in Kähler modular space, subject to this constraint that the Planck to string scale ratio is constant, have been classified. Here we will focus on something that they call type A, where essentially the Kähler form of the base B3 can, in the asymptotic limit scales, like we have scales that one Kähler cone generator has a Kähler modulus that blows up, which is then compensated to ensure this constraint by blowing down certain other Kähler moduli. And this special Kähler cone generator, in order to satisfy this, has to satisfy that its triple intersection is 0, and that and for it to be a type A limit, that the triple intersection with one of these shrinking or one of these Kähler cone devices with a shrinking Kähler modulus has to be unequal to 0. And one can now look at the curve J1, which has a non-trivial normal bundle, which shrinks in the limit, in the asymptotic limit, where we go with lambda to infinity. And one actually can get or one has the case that C0 is a fiber of a rational vibration. So similar to what I had on one of my first slides for the 60 case, where we now have a rational vibration of this curve C0 over some base B2. And now wrapping a D3 brane on this C0 gives rise again to a critical heterotic string now in 4 dimensions. But this entire discussion is purely classical, and we can ask again what happens, or do quantum corrections affect this limit? So the first question is, do we expect quantum corrections? Of course, first there are, for instance, D3 instantons along devices which are essentially the pullback of the rational vibration of curves in the base twofold. They become important, so they shrink. They have a vanishing action asymptotically. So one can ask, do we get a superpotential here? And we again have the asymptotic hierarchy that the tension of the D3 string wrapped on the C0, which gives rise to the heterotic string, has a tension which is much smaller than the KK scale. So we see that the limit should be obstructed again. So there are now two possibilities since we're in n equal 1. So either the emergent string limit is dynamically obstructed, so that the divergent potential is generated that shields the infinite distance points, or the classical limit is kinematically obstructed, so it does not actually belong to the quantum moduli space, as was the case in the type 2a discussion here and in our discussion in the hypermultiplied moduli space. So we will check for possibility 2, because this was also the case in the end, and due to time reasons, I will give you the answer straight away. So does the classical limit exist as a limit of the moduli space? So the intuition from the analysis, for instance, in type 2b that I told you before, we can have obstruction due to non-zero quantum volumes. So the first question one could ask, does C0 have a non-zero quantum volume that leads to obstruction? And this is actually not the case. One can look at the, for instance, sigma model volume of C0 by a fourfold mirror symmetry. And let's consider a very easy example where actually our base B3 is just a double rational vibration. We shrink this curve and we blow up this curve, which is essentially this limit. And then one can look if this in this limit, or one can first look if this this upper P1 actually has a non-zero quantum volume by looking at the discriminant volume and seeing that the singularity close to the point where one would classically expect the fiber to shrink to 0 size actually splits, which indicates by an old argument by Meyer from 1906 that there is a non-zero quantum volume. However, this non-zero quantum volume scales is exponentially suppressed in the volume of the base P1, and so that actually the non-zero quantum volume is there, but is not enough to obstruct the limit. So how do we get then our obstruction? We should, since we're doing F theory on Calabi-Yau 4 force, we should actually look at the volumes of the base devices, because these are the actual physical Kähler moduli, or physical moduli that enter our action. So we can translate now our limit into a scaling of these volumes of base devices, and we see that the one which is associated to the special Kähler cone generator J1 shrinks, while the other ones which are associated to the Kähler cone devices that have non-zero intersection with C0 grows. Since we know that we have a critical heterotic string, we can use F-theory heterotic duality to identify the moduli, saying that this effectively gives us a heterotic Kähler modulus, and this gives us the heterotic 4D dilaton, this combination. But now we know that, now it is known, thanks to these people, that these coordinates actually receive perturbative alpha prime corrections, which are of this form, where the essential ingredient is this integral over the third Chern class wedge the corresponding divisor that we're considering. So if we now say, okay, we only have one divisor that has a non-trivial intersection with C0, so which is essentially the case if our dual heterotic theory is perturbative without NS5 branes, or this is one case where this happens. We can translate everything. We can look at the scaling of the alpha prime corrections in this limit, and we see that actually everything is encoded in this particular correction, which is the integral over C3 wedge J1, which is the special divisor that has triple self-intersection 0. One can then actually show that if our B3 is weak Fano and we additionally assume that we have a smooth Weierstrass model, this chi1 is always smaller than 0. So at some point along the trajectory, the alpha prime corrections, this tells us if we plug in the scaling limit, are bigger than the classical contributions. So we see that along our trajectory at this order in alpha prime, we would expect that the real that this modulus becomes 0. But we identify this modulus with the heterotic 4D dilaton. So one way of thinking is that actually we cannot trust the heterotic F duality in this limit because we get so heavy corrections to the map that that it is actually not sensible to talk about this. One other way to think is that the string from the rep D3 brane does not become weakly coupled, and it is not even clear if it is stable in this limit that we're taking. So we see that the classical limit is obstructed. So we don't necessarily get an emergent weakly coupled heterotic string because we can simply not trust this limit. And this is furthermore not even clear if we're at infinite distance, because somehow we are going to a non-perturbative region of this of our theory, and there it is not clear how to measure this distance. So, but to stay in the controlled regime, we can say, okay, we can change our limit and rescale it. And what we get is that we get if we rescale it in this way. So, and most importantly, we still have the possibility that this fiber C naught, whose volume is just given by this Kähler modulus, can still shrink. And in this limit, we get a weakly coupled heterotic string, and we can actually say that this limit is not further obstructed. We're keeping all the other moduli, or this special modulus, we keep it constant, and we ensure that we have the hierarchy that we need to have a sensible emergent string limit. On the heterotic side, this says we're essentially just taking the weak coupling limit and staying at finite distance in the Kähler modular space. But at the same time, we see that a non-perturbative superpotential, which generically will be generated, as I said before, but this is not divergent. So that also therefore, this actual emergent string limit, we don't expect further abstraction by a superpotential. So, and in total, this pattern is very similar to the type 2B hypermultiplet discussion. We see that the quantum corrections enforce the correct hierarchy and give us a genuine weak coupling limit, in the sense that we actually just have a weak coupling limit and not take any further limit in Kähler modular space. So, and these are my conclusions. And so basically that we investigated the role of quantum corrections for infinite distance limit with these emergent strings in 4D with n equal 2 and n equal 1. We saw in the type 2B hypermultiplet sector that there's an interplay between d instantons, which we captured by mirror symmetry. And in the F theory case, we saw that this is actually perturbative alpha prime corrections. And in both cases, the quantum correction ensure the correct hierarchy, though in F theory only worked at order alpha prime. So this is all I have to say. Thank you.
Thank you very much, Max. Questions for Max? First one from Irina.
Hi, Max. Thank you for the talk. It was very nice. I have just a question about the last thing. So, do you find any correlation between this kinematic or dynamical obstruction because of the superpotential? I mean, if you find that there is no obstruction in terms of the Kähler potential, then will that mean that there is no obstruction from the superpotential, or not necessarily?
So I would say that we saw this obstruction because we saw that this limit that we want to take is not part of the we cannot trust it because we go outside of the region that we can capture by our geometry. And I would say that in this case there's also, since we are staying at finite distance in some sense in the heterotic Kähler modular space, I would say that there is no that this obstruction actually ensures us that we cannot have a non-perturbed that this obstruction ensures that our emergent string limit is not dynamically obstructed by a superpotential. So I would say this is actually related. I don't know if I answered your question.
Do you think it's related in this particular case, or is something more general? I don't know.
I think it's more, I would say it's more general, but I think this was a particular case where we looked at this F-theory compactification. But I would actually say it's more general because this would also imply that our scalar potential cannot diverge towards infinite distance, right? And this, I think, is in agreement with the de Sitter conjecture, right?
Yeah, that's what I am asking. Yeah.
Okay.
Any further questions? Okay, if not, let's thank Max again.